Right, folks, good afternoon. Quite a crowd on a Monday afternoon. Thank you so much. My name is Prithvi Raj. I am a senior community manager and dev advocate at Mirantis. I'm also a CNCF ambassador. The journey started 5 years ago with a lot of chaos engineering, but I am right now working on a lot of platform engineering with K0S and Coordinate.
Great. And my name is Cortney Nickerson. I'm a longtime advocate of open source communities. I'm currently head of community at Nirmata, the creators of Kyverno. I, like Prithvi, am also a CNCF ambassador and got started in this space through writing a newsletter for a community. And I'm very thrilled to be here today.
All right, folks, let's address the elephant in the room. People have started to ask if DevOps has become DevOps. That's the primary question that I hear lately. And to be honest, even if we talk a lot about platform engineering, I believe DevOps can never become dead, given the adoption, given the fact that people are still adopting DevOps even before reaching platform engineering. I believe people have not reached the right way to implement the DevOps practices, starting to scale. We expected developers to handle infrastructure details, YAML sprawl, dozens of tool chains on their own, and then we hoped that SREs could, manually review them, bring in ad hoc policies, SLO, SLIs, managing them. But the reality is that we haven't been able to scale. Human approvals have made it a lot of, they caused a lot of manual ticketing. And developers just want to ship code. They want to write code. And, operations team have been tired of becoming, the ticket clerks of today. And that is where platform engineering emerged. The idea was to productize infrastructure and deliver it as a service. And as I spoke about, DevOps challenges brought in the idea of platform engineering. DevOps was supposed to bridge the gap between developers and operators. But the challenges have continued to slow down teams. Slow onboarding remains a problem. Developers still spend days and weeks waiting for the right environments, permissions. And when they finally get access, they are overwhelmed with the complexity of the infrastructure itself. And developers don't want to become infrastructure experts. If you have been seeing a lot of talks around KubeCon or the co-located events itself, developers are asked to learn the CNCF landscape. And I personally have to use a microscope to zoom in through the CNCF landscape. So these pain points are exactly what have driven organizations towards platform engineering. I believe folks who have attended the Platform Engineering Day have seen a lot of talks around platform engineering, so I won't be taking a lot of time around why consider platform engineering. But yeah, there were clear practical reasons to invest. Of course, agility, you need to reduce your critical incidents and application downtime by giving developers a stable, consistent environment. Cost, of course, underutilized resources waste money. Without a platform, you often provision to stay safe. You need to standardize the process for security and compliance. Ad hoc scripts and tribal knowledge don't pass audits. So, of course, by adopting platform engineering, you are gaining reliability, visibility, speed. You are able to self-serve your developers and make things simpler for them to ship code.
So that brings us to the rest of our talk today. Today, we're going to have you picture a modern international airport. And the whole reason for this isn't because your flight was probably delayed on the way here, but that will have something to do with it later. But it's to explain why platform engineering is no longer optional for modern teams, but rather it's now become a necessity. So let's dive into the airport analogy very quickly. Each airplane in our analogy is going to represent a platform or an actual environment where applications live and run. And logically, your developers are going to be your pilots. They're the people who are navigating these platforms and delivering value to your customers. And then your platform engineers, with help from the control tower, which we'll talk about in a minute, and the ground crew, which is also a hugely important component, ensure your flight is safe, it runs efficiently, it stays compliant with regulations. And so our mission in this case is to enable pilots to fly very quickly, reach their destinations without collisions, without delays, or without safety incidents. So when this is done right, and we've all gone through international airports that work incredibly well, the entire operation runs very smoothly. Planes take off on schedule, routes are optimized, everyone lands safely. It's really a lovely experience to take a flight that way. So achieving this level of coordination, however, requires a lot of sophisticated systems, clear protocols, and consistent vigilance. And so it's not enough just to have an airplane. It's not enough to just have a platform. It's also not just enough to have somebody who knows how to fly an airplane or have a developer who knows how to build an application. You actually have to have a way to manage the entire fleet. So imagine the airplane as your platform. Running a platform today means coordinating hundreds of services in a single flight. Hundreds, not just a couple. Hundreds. That's a lot of things to coordinate. So you've got to think about your secure software supply chain, observability, FinOps, resource management, networking, secrets management. The list goes on and on and on of things that you have to be able to manage. And each of these services is like a different subsystem on an airplane. Engines, navigation, communication, fuel, all of these things have to work in coordination together in order to be able to create a reliable flight or system. So in a modern platform, it's much more than just Kubernetes as well. It's the entire operating model around Kubernetes. So just as a pilot trusts that the autopilot or their instrumentation is going to work, developers need to be able to trust that the platforms that are underlying the components are configured the way that they need them to be, that they're kept secret without having to constantly have somebody intervene to make things work. So that brings us to the fact that developers don't build the airplane. They might be flying it, but they don't build it, which is why you need a platform team to actually do this. Developers shouldn't always be asked to build the airplane or what they even want in the airplane, because a lot of times they don't even actually know. Sometimes they do, sometimes they don't. Sometimes things need to actually be coordinated by somebody who can see how those components need to fit together. The platform might be running on KOs, it might be running on K3s, it might be running on vanilla Kubernetes. None of that should actually matter to the pilot. So instead, we need to give them a single user interface that abstracts away all of the complexity of those issues and let them file a flight plan or a request for an environment, one that's going to work, one that they can trust, and one that the control tower and maintenance crews can provision and make sure that it's safe and compliant aircraft. Platform engineering is going to decouple the developer experience from underlying implementation, and that results in a much higher productivity from your team and fewer crashes in flight. So the reality of platform teams, feels oddly similar to the different delays and cancellations that many of us experienced on our way here today through the airline industry. So tickets pile up in backlogs, clusters run completely unchecked, compliance gaps emerge, and there's way too many disparate tools that are not unifying in terms of the actual flight plan that people need to follow. Platform engineers are constantly under mounting pressure to deliver things faster, safer, maintain control, and that becomes really, really complicated. So they end up spending more than half of their time, and we're constantly talking to people who spend more than half of their time just managing configurations. So nearly half of platform engineers actually say that compliance, cost, visibility are their biggest blockers in anything that they're doing. And similar numbers feel forced to even have to choose between speed and compliancy. And we hear this all the time. Well, if you put too much compliancy, it slows everything down. But if you speed things up too much, you end up being incompliant. So these are things that we want to discuss today, because oftentimes we also see environment sprawl. So hundreds of clusters that are spread across multiple clouds, each are configured slightly differently, configuration drift starts to create inconsistency, which then creates risk, and all of those things just build and build and build to then cause delayed flights and a lot of chaos for people. Translating platform challenges to the airport, it's a very similar use case. So every platform engineering challenge has clear aviation equivalent. I'm going to look at some very, very clear ones. When you have cluster sprawl, it's too many clusters with no coordinated schedule. It's like having planes that are lined up on the runway just sitting there and not actually being able to take off, causing delays. Policy drift is where you have rules that aren't consistently applied across clusters. It's like totally skipping your safety checks before you even get on the airplane. And eventually, if you do that, you will end up having an incident. Limited visibility is also something we hear people complain about. It's like having your tower completely lose a radar contact with half of the fleet. You can't fix what you can't see, and we constantly hear platform engineers asking to have more visibility into things. Recognizing these parallels helps us see why traditional approaches are starting to fall short as people continue to scale their fleet, and why we need better systems.
So what does a real platform look like? This is how we have somehow tried to manage the components of a platform. You need your pipelines and GitOps in place. CI/CD, of course, are foundational. You need an internal developer portal that surfaces approved services and patterns. You need standard processes for environment provisioning and teardown. In many organizations I see in the community itself, people I talk to, these pieces exist, but everything is scattered. Developers are bouncing between Git, Jenkins, GitHub Actions, service catalogs, monitoring tools, tickets, and different kind of tooling. They want to apply something, but there's no budget, or things are everywhere, all over the place, and basically a Kubernetes tooling sprawl. And platforms need to be democratic. I mean, even before you start implementing platform engineering, I believe platform engineering has evolved through multiple stages, from the separation of development and ops to emergence of DevOps to eventually platform teams. But obviously, to address this, I believe CNCF has put a lot of effort. We have seen platform groups emerge, emphasizing on collaboration between different teams, and creating some sort of a role between producers and consumers that can bridge these rigid boundaries. But I believe that a platform democracy has to be a model where all stakeholders, developers, SREs, security teams, external providers, and even your customers have to come in and bring in that sort of a shift, that sort of a model where you are redefining the roles. Producers can no longer just be the platform team. Your consumers have to come in together to make a platform group or make platforms democratic. And platform engineers are the ones who are building these airplanes. They need to support multi-cluster configurations. AI/ML workloads are the reality. Hybrid multi-cloud deployments. I haven't seen a large organization hosting their environments on one particular cloud. I talk to anyone and they are like, we have our environments on-prem. Some of them are on public cloud environments. We are using AWS, Azure. So building a safe, reliable airplane means accounting for all these factors. Platform engineers design wings, engines, navigation systems. They provide cockpit instrumentation so developers can operate the system. So you need to ensure that you have the right multi-cluster configurations and you are able to manage them well. But multi-cluster platform engineering throws its own challenges. Obviously, the best practices could be having a single application per cluster in isolation, having the hybrid multi-cloud model in place, have dynamic on-demand clusters to ensure that your resources are optimized well. But with multi-cluster deployment comes the challenges of Kubernetes sprawl, inconsistent workloads, and a risk of non-compliance and complexities. So how do we address this multi-cluster, multi-cloud sprawl challenge? Let's talk about one of the main aspects of controlling your airplanes, the control tower. I would like to introduce to you an open source tool that went GA this February called Cordant. It's the control tower which knows every plane, every route, every gate assignment, and that is what Cordant does for you, ensuring that every environment has a defined path, proper lifecycle management, and complete visibility across fleet. The idea is to coordinate operations by orchestrating orchestrating multi-cluster deployments, managing schedules across the fleet. And obviously, with Cordant, you don't have ungoverned clusters or manual checklists that you need to automate. So this is what the architecture looks like. It has three major components. The cluster manager, which is using cluster API under the hood, but also uses Cosmotron or the Cosmotron controller, which helps you have a hosted control plane. So basically, your cluster API controller is interacting with your systems or your Kubernetes deployments. And you have the state management, which is using SwellTOS under the hood, which helps you manage the add-on states or add-on controllers. So when a new request comes in, Cordant uses a declarative templated model to spin up the infrastructure in the right cloud and region. And it integrates with your CI/CD or your service mesh to ensure that your deployments, your pipeline, all of them are in place. And later we'll see how we are integrating it to Kyverno from a policy enforcement standpoint and compliance at each and every step. So this is what the future of Cordant looks like. This is a little bit about Cordant AI, which is helping you, address challenges on not just on a public or private cloud, but a GPU cloud as well. We are having a composable architecture. The idea is to provide clouds with optionality and choice. You can pick and choose your stack components. It has a true tenant isolation, and obviously you can integrate it with your own services, ensure that your environment is operating as expected and having the services that you want. So as I spoke about, it follows a templated approach. So it has service templates which are commonly used as beachhead services. Say you want to use a cert manager, a CSI, CNI, service mesh, if you want to use Linkerd or Istio. So anything can be pulled in as a template, which is a predefined YAML. And similarly, we have a predefined YAML for Kyverno. All of this is part of the beachhead services. You have a cluster template as well, but we'll talk about the service template, which is eventually also going to be the Kyverno service template that can be used in a use case. So you can be deploying it using a Kubernetes manifest or a Helm chart. It is basically a YAML file where you apply your service spec, your kind, your API version, and this guarantees repeatability and consistency. If you are using a Cordant Service Manager template, you are eliminating basically a configuration drift or a manual error.
So now that brings us to our safety crew and the people who are making sure that your flight is compliant and up to policy. And like Prithvi was saying, it incorporates perfectly well with the Cordant templates. Kyverno, if you haven't heard of it, is an open source project on the CNCF landscape. It's the most widely adopted policy engine built specifically for Kubernetes. While it can be used in other environments, its original purpose was for Kubernetes workloads. It validates, mutates, generates, and even deletes resources that become stale, and you can create your policies in the familiar YAML declarative format. You don't need to learn a new programming language in order to use it, and you can simply write your policies as configurations. Kyverno has recently introduced 5 new policy types. Those are common expression language-based types. So those cell policies are now validating policy, mutating policy, image validation policy, which is a crowd pleaser and favorite, generating policy, and deleting policy. And these new policy types really do speed up your policy processing. It makes it easier to express complex rules. You can express them in cell, which has now been widely adopted by Kubernetes, makes everything run exponentially faster because they're all using the same language and they're all declarative. And with Kyverno, policy isn't an afterthought. It now becomes something that's built into your platform, and it just automatically runs your safety checks on your plane. So you can think of Kyverno as your policy autopilot almost. It enforces guardrails, it's going to audit your configurations, it automates security, it optimizes your resources, it optimizes cost savings. You can use policies for literally any problem that you might have in your platform to help figure out how you need to fix things. It's going to validate incoming manifests, it can mutate them to include required labels to make sure that you have your labeling conventions used correctly. It can even generate additional resources like configuration config maps, and RBAC roles. Kyverno automates security best practices in a very simple way. For example, you can use it to ensure containers don't run as root. And you can use file systems that are read-only. It's going to automate your operational best practices. You can truly use policy for just about anything that you might need within your platform. Now, let's jump back to the airline analogy for just a second. Platform teams have their own routine flights. They need to provide self-service environments so that developers can move quickly without having to wait for manual approvals. They don't want to end up being the bottleneck in that process. So they need the built-in security enforcement. They need the built-in generated manifest. It's not optional. If it has to be manual, then that is a problem because you're supposed to be automating things by default. So they really do become part of your fleet-wide governance to ensure that your policies are consistent across hundreds of clusters. Platform engineers also need automated management for edge and AI clusters, and we're going to see those starting to pop up more and more, which is why it's a really good idea to start getting started with policies now. The Cortney-Kyverno combination makes all of these everyday flight routines exponentially easier because developers can now onboard new projects very rapidly. Security checks happen automatically, policies are enforced consistently, and really your tower and your security crew, both on the ground and on the plane, are able to communicate with each other all the time. Let's take a look at our use cases for 1 second. We're going to show one very clear use case. So for self-service platform provisioning with guardrails, in most organizations today, developers might have to wait 3 to 5 days to get a new environment. That's quite a lot of time. They submit a ticket, ops manually provisions their infrastructure, security reviews configurations, and eventually somebody remembers to tear down the environment after they've used it. Meanwhile, configuration drift starts to happen, inconsistent policy enforcement starts to happen, it all becomes a risk. So our goal here is to provide standardized, secure platforms that give developers autonomy while they're maintaining oversight. You can very much think of your developer as a pilot who's filing for a flight plan for a short haul journey. And right now, the simple request involves back and forth ticketing. It automatically becomes something that just spins itself up. Now, imagine your developer. We've got Alice. She's a developer, or she's our pilot, and she's working on the Team Alpha project, and she needs a sandbox environment for 72 hours to test a new feature. Today, she would have to open a ticket, describe the environment, and wait. Pain points around all of that are manual provisioning tickets, inconsistent configuration, configuration drift, policy violations, and so on. Our goal is to spin up all of that for Alice so that she can file her flight plan through a portal and have the environment provisioned automatically. We want guardrails and policies in place. We want to make sure that we have image restrictions and that she gets approval for everything she needs in less than 72 hours.
So let me explain it in a minute in 3 steps. How does step 1 work? Of course, Quadrant is the control tower. Alice is submitting her request, and Quadrant pulls up a cluster template, provisions the infrastructure. You can use infrastructure as code as well using Crossplane or Tofu. It notifies your CD, Argo, or Flux to deploy your baseline services. You can pull in your policies, your RBAC controls, monitoring agents. Because of course, these are defined as version templates in every sandbox environment, fully configured and compliant, delivered directly to Alice, no human ticketing route required. And because that environment inherits standardized labels like team owner and TTL, the platform already knows who owns it and why does it exist. Before any workload group leaves the ground, Kyverno performs comprehensive inspection, policies, defining the required metadata, such as team owner, cost center, and TTL. They enforce the resource limits on the CPU and memory to prevent exhausting the resources. And they only allow images from approved registries and ensure containers run as non-root with read-only files. Testing, of course, is automated. The Kyverno CLI provides quick validation in your CI pipelines, catching issues before they hit production. Chainsaw runs the full scenario on an isolated cluster or a production environment, and only workloads passing all checks proceed to deployment. Once this environment is live, the monitoring comes into place, the dashboarding, you are continuously able to watch your fleets, your policy. Prometheus provides real-time status, and when the TTL expires, in Alice's case, say 72 hours, Cordant automatically decommissions the environment, reclaims the resources, and prevents the forgotten clusters from driving up costs.
So we're just about at time here, but you can see very quickly that all of this results in a workflow that's much more efficient. It gives you visibility into what's going on. It builds in your security very quickly, and it gives you immediate results that are actionable, not just for your pilots or your developer team, but also for your platform team to be able to make things run more efficiently. All of this matters because it's going to make your life exponentially easier. You've got an entire ecosystem of tools, including Argo CD, Prometheus Crossplane, a whole set of Kyverno tools and Cordant tools that can help you make this possible. And you can make more advanced flights as well as go on to final destinations that are far more complex. So if you want to get started with us, you've got a boarding pass. We're here all week. You can ask us loads of questions as we go on, and you're all cleared for takeoff to make sure that your teams get to their destination safely. Thank you.